sort of recall the Potter-Tate exact sequence. So my F is a number field. S is a finite set of places, including those including those dividing L in infinity. Okay, and M will be a finite length O-module with continuous action by the Galois group. So this is the Galois group of the maximum unramified extension of F. That's unramified outside of S. The maximal extension of F. That's unramified outside of S over F. And the Potter-Tate exact sequence. Is it weird? Like this sound? Maybe just me. So the only way I can remember how to do this is write this as if we're going to do a long exact sequence. And we're going to do H0 of GFV of M, H1 of GFV of M, V in S, H2 of GFV of M. And somehow by duality, this H0 is dual to the H2 of the dual. So I have the restriction map. Now it's dualized. And the 9-term long exact sequence goes as follows. With one small change, which is that this is considered the Tate cohomology when my V is Archimedean. In particular, for the real, it's always sort of a two-torsion group. And when V is complex, this is trivial. Okay, so this is basically our goal today. But we're not, so in fact, the goal today is to prove this when, maybe I should say here that my O is in a coefficient field I denote by E, and this is over QL. So when L is not equal to 2, we're going to prove this today. When L equals 2, somehow the method I used to prove this, I couldn't make it work, unfortunately. But we'll see. So last time, towards the end, I recall a bit of things from class field theory. Since I already deduced this, so let me just sort of say what I got. If I take the ith cohomology of the ELs modulo the global elements, if I just only care about the ZL part. So last time when I wrote it, I wrote the test ZL inside. I think it doesn't matter, but I wrote, I guess let me move it outside, just be safe. So this is if I equals 0, this is F cross AF cross together tensored with. Basically, this means that I only care about the L-ID part. Other parts, I just sort of killed it. For, I guess, I equals 2, this is QL mod ZL. And others, we talked about this is 0. I want to use these as input from global class field theory. Next, so when we somehow separate this, so the next thing I want to do is that I want to change this a little bit. Essentially, I want to do this. On the other side, I want to quotient out by basically all the local terms, so unramified part of this, or sort of integral part of this. I think this is a better way to write this. So basically, I want to quotient out inside of here the integral part. But then you see that when you do this sort of, if you take it down and turn out integral part, it's an infinite direct sum of things. That's a bit annoying. So I want that to be, but on the other hand, so this quotient basically, what you see is basically somehow generated by uniformizers, and it should be killed by things over the side. And so therefore, it's natural to kind of guess that if you make the quotient on this side completely integral, you can ignore this quotient here. Let's see what I should write. Okay. So that's my claim. Okay. So let me prove this. I mean, I guess when I start to prove it, you kind of understand how this comes out. So if L is a finite extension, finite sub-extension of Fs over S. So I want to take a finite extension of F that's sitting inside Fs. Then what do I have? Then I look at this. So start with AL cross. On this side, I want to quotient by L, and on this side, I want to quotient by the product of all the elements that's not in SL. I'll say what SL is in a minute. So SL is all places of L over S. I give a set of places of the base F, then for any extension of this F, I can look at the places above those places. So I want to quotient out by the integral elements in those places. And on the other side, I want to somehow kill the places that's inside here. So if I do this, what do I get here? What I get here is somehow the quotient. What's the quotient here? So the quotient here will be L cross over AL. Let me write this sort of away from SL cross and quotient by this. Right? And this quotient is nothing but just a direct sum of all the places in SL, but not in SL, where it just takes a uniformizer to the least power. Right? Because this is just basically a restriction product of LV cross. And somehow the quotient is precisely just looking at the valuations of the corresponding term. And the left quotient by L means that this is sort of, you can think of it as sort of fractional ideals, quotient by principal ideals. Except I'm not taking all the fractional ideals. I'm taking only those fractional ideals generated by places away from SL, and then quotient by global elements. So this is, oh, sorry, this is not, my bad. This is a co-kernel of this map, not isomorph. So this can be identified. I'm going to write ideal class group of this. So this is basically taking all the fractional ideals generated by the places away from SL, quotient by the principal ideal. So that's just ideal class group. In that case, we know this is finite. And we also know that this is, let's see, it feels like this is going to be a subgroup of the ideal class group because it's generated by places away from SL. So this will be a subgroup of the big ideal class group. Okay. So that's the quotient of the exact sequence. So look at the sort of this side. I take the places at SL to kill, I guess, inside of here, the SL part. But then what's the kernel of this map? Kernel of this map will be elements in here that maps into L cross times this thingy, right? But this has nothing to do with this. So basically, you're looking at elements in here, which are global elements. At the same time, they have no valuation at places away from SL. So that's just nothing but sort of OL, 1 over L, how should I say this, SL. So when maybe I should say, whenever I write this, I mean to say that I take global elements which has valuations only at places dividing SL. So we have an exact sequence SL. Oh, cool. Yeah. Right. Multiplication. Thank you. Thanks. Okay. And now I regret that I put my. So let me erase the top part of this. I'll write a bit and then move back to the other side because I want to keep this for a little bit longer. Hopefully. Maybe I'll give up. You know what? Let me give up that. So yeah, just in your mind, memorize this. The night term. We'll come back to an exact sequence which looks very much like this one shortly after this discussion. Okay, so now I want to take limit. Take direct limit over all such L. But there's a fact that if you take the limit over all L, this ideal class group is trivial. Somehow in the limit, this ideal class group will die. SL, or SL and S same thing, I think. The reason being that I'm taking the limit over all extensions that's unramified outside of S. In particular, at some point when I see an L here, I will definitely at some point take the limit over its Hilbert class field. There's a statement that every ideal becomes principal after you pass the Hilbert class field. So I just sort of, so in the exercise I kind of explain a little bit. So I just sort of skip that small part. And then once you take limit, so this side, I guess once you take limit, you see that this side becomes the right-hand side here, whereas this guy becomes this one. So I'm done. That's just sort of a tiny thing I have to kind of handle. Okay, now. I computed the cohomology of this guy. Now I want to compute the cohomology of this guy, which looks a lot more finite than the other one because see, there's only kind of product over sort of finding many places in some sense. Whereas so essentially I want to compute the cohomology of this guy. So what I want to do is I want to take one goes to the product of all the V not in S of O F so V goes to so let me write this, what I want. Cross. So this is last bit of technicality we'll have to deal with before moving on to the more, I guess, elegant part. Right. So we have this, and then we take a global cohomology. So Galois cohomology. So I get 1 goes to, so this is product of V and S of just OFV cross. And this part is just F cross. And this is the cohomology, sort of invariance part of this. Let me just write H0. Give it a name. It's a bit long. Give it a name. I don't know what it's called. J, say, JS? Maybe JFS? How about that? I don't know what it's like. I just think of a name. There's no reason I call that. Sorry. Now H1 of this guy. As I come around, I'm looking at sort of H1 of this guy. So one of the things I want to point out is that what I do here is I'm taking the extension of this F inside a maximal extension of F that's outside of S. In particular, at places away from S, I'm taking only the ununified part of the extension. So in some sense, I'm taking this, but then I'm taking H1 of sort of FSW of some places. But the point is this is unramified. Okay? The point is that this thing is unramified. And the point is, I guess I'm not sure if you know this. So if L over K is unramified locally, local field, I guess this is trivial. The reason being that you can first of all show that you can show the residue field cross is trivial. This is Hilbert 90 for the residue field. And then, I mean, basically you filter it by the valuations, by somehow 1 plus var pi L, it's unramified, so it doesn't matter. Var pi K or var pi K are the same. So OL to the mth power cross. You filter the thing by these subgroups. And all the subquotients are of the form either that or KL, the additive group. But both of these are, okay, 0 maybe. Let me call it 0. Because 1 equals 1. So because all the residual parts are sort of 0, therefore as you take completion, this whole integral cohomology is 0. So therefore this is 0. And then this is the H1 of this guy. I'm already computing over there. Maybe secretly, let me tensor everything with ZL. Because I only care about the L-adic part, and I only computed the L-adic part anyways. Now, what is the H1? H1 is 0. Okay, good. H1 is 0. Now I get to H1 of this thing. Just remind you again, this is not standard notation. I just want something. Maybe write ZFS so that it's not equal to anything that we usually have name for. So that doesn't cause confusion. Okay, coming over here. I mean, this is the unramified extension. The Galois group is a procyclic group. So there's no hierarchical homology. This is 0. And what I have over here is H2. So I get QL mod ZL. So that goes to H2 of GFS, ZFS. And the rest are all zeros, because this is all 0. And by that, but what we recall from the global Cost-Field theory, all the middle column are also 0. So these are all 0. So we computed this guy here, the cohomology of that. Let me write it clearly here. Or you know what? Let me write it over here. So So what I get is that over here I had get the integral version of this result, which is that, oh, I shouldn't have, let me just write down what I really get. So I get F cross over AF cross over on the other side, the product of all the places away from S, OFB cross. This is I equals to 0. And let's see, so the first column is 0, and the second column is this. So nothing changes except the first one changes. Of course, you can, I mean, this one is roughly the same as OF 1 over S cross over product inside of here, but off by a ideal class group of F. So let me not do that identification, just this. Keep the ideal class group in our discussion. Okay? So that's good. Erase this. So that's the only, okay. We've come through the most difficult part of today's talk. Okay? Well, let me make a remark regarding this. Oh, this is the only thing I need to ideal class group, I guess. So I want to remark that using this, I can use this to compute. Because somehow the cohomology of this one I know relatively well. It's a local cohomology computation. So I can compute the cohomology of OFS. So this is sort of the integral version of the multiplicated group. And once I computed this, I can further compute HI of GFS of mu L from this one by a variant of a Kummer theory that 1 goes to mu L goes to OFS. This X goes to X L's power. So I can use this. I can use this to compute this cohomology by Kummer theory. Here, maybe kind of the key point of this discussion is why not using why don't we just use this? And why do we have to go through all this trouble? Why don't we just sort of simply use this to compute the cohomology of mu L in some sense? The answer is you can't quite use this. Here's why. Because it's not surjective here. See, like if you pick an element in here, say A here, whose valuation at some place, say P, or P not in S, of A is 1, then there's no, like if you want to find an element in here whose L's power is this A, you have to make an extension which is ramified at this P. But my Fs means that my extension cannot be ramified away from S. So therefore, this is not exact. This is sort of not surjective. Because somehow, like for those elements in the image, they have valuations at places away from S, has valuation at least divisible by L. So that's not surjective. So that's why we have to kind of go through all the trouble to make all these sort of integral version. Because for the integral version, it is, I guess, it is surjective. Whenever you have an element here, I guess it will not ramify away from, because there's no valuation at S, away from S. So it should not ramify at S. But maybe only trouble is this L's power, but L is already in S, so we allow it to ramify at S. So this is surjective. Otherwise, somehow the non-integral version is not surjective. But we're not gonna, but for in the proof, we don't have to, later for all the characteristic, we need to use this a little bit. But for now, we don't need this. for proving the prototype exact sequence, we don't need this yet. Yes. Okay? I hope I explained clear. So why we go through this trouble to, or rather somehow sort of dirty work to make this work, to make this thing. Just a comment that, in mathematics we always ask why we do the things we do. So that's somehow important. Now let's come to the second technique we're going to use to prove prototype exact sequence. So we need some homological algebra technique. In my opinion, this will simplify the proof of the prototype exact sequence. So first, for a complex C dot dC dot, okay, of OE modules and an integer. So we can shift the complex to the left, I guess. So I can change the complex a little bit. So that after the shift, the ith degree is the original n plus I degree. And of course the differential is sort of the same thing with a space. Not quite. To properly make things nice, I need a sign here. But this is just to make a lot of things work properly. For all the differentials, I put a sign here. If I shift by 1, all the signs go to minus sign. But it doesn't really matter for cohomology that much. This is just a convention. How to memorize it? I don't know. This probably looks very straightforward to you. But when I learned this, I use some sort of Chinese word. So 这个括号是左加右减，然后所以你如果是正的话，就是往左边移。Anyways, that's my way of memorizing it. It won't work in English. Anyways, this is so true. But now I want to explain. I assume everyone has learned a little bit of homological algebra, has certain degree of comfortable working with sort of these complexes. So I have a morphism of two complexes is a of cochain complexes of OE module. Then I want to define the following. So-called the cone of this map. Maybe I just define fine, I'll just define cone. I should define fiber. So the nth degree is this guy. Okay, so the nth degree is Cn plus 1 direct sum. I read it vertically, so this is one term. And of course the n minus first degree is this guy. And the okay. Now I have to specify what the sort of the differential morphisms among them. The way this is done is that on the top, I always take minus dc, and at the bottom, I take dd. And of course, I have to encode this information of f inside of here. So I take F here. So we know, let's check that this is a complex, okay? So if I start with an element in here, that's very easy. If I d it, it will just, so going from here to here is trivial. So this is zero map. So I don't write that. So let's check this is a complex by just pointing things on this diagram. So if I start with something in here, I take differential, so it doesn't map over there, so I just map here. And the next thing, differential again, you get to here. So that's the same as on the D, you differential twice, you get 0. Okay? Now if you're on C, so it has two parts. One goes here, one goes here. The part goes here can also continue to here, but this 2 differential is 0. The other thing goes here and then you D. And you have also a thing here and then down here. So it's a question of, if you have an element in here, right, you can go this way and go this way. If you sum them up, whether you get 0 or not. But then, so that's why I put the negative sign here, because FD is, so FDC is DDF. But if I have a negative sign here, if I have an element here, then this way is a negative of this way. So they sum up to 0. So this is a complex. Just leave it to you to check it again. Okay, so when you have this, let's see. What am I writing here? Once you have this defined as cone, we have an exact sequence of complexes. Let me put a cone dot here. Unfortunately, I'm going to write this. So this is defined horizontally. Now I'm going to turn the picture 90 degrees. I'm going to write it vertically. C twist by 1. Okay. So what is this exact sequence? Let me write it down explicitly. So this is 0 goes dn, goes to, so the degree n term is these two, right? So cn plus 1. dn. This goes to cn because it shift by 1. So the nth, what's it called? The nth degree n term is the original degree n plus first term. And let's also check the differentials. So let's see. Cn plus 2. Okay. Remember that. So okay, this is dd by definition. This is dc by definition. So let's check this the middle term. Let's try the diagram commutes. So let's copy down the middle terms, the differential. So this is negative dc. My bad. Negative dc just reminded me, because shifting by 1 over here, I define it to be you have to change the sign of the differential. That's to somehow, partially to make this work. Okay, on D side, this is just dd, and then you have this cross F. Okay, so let's check that this is a commutative diagram. So if you start with something in dn here, right, go down to differential, and go over here, you just only map to the D part. So that's a differential downward. That's okay. So if you have this map, if you start with something in here, but when you map over here, I only care about the part on C. So D part got completely killed. So an element in here can map to two coordinates here, but somehow this part is completely killed. So you only see the minus DC part. So that's a commutative diagram. So from this commutative diagram, we get a long exact sequence, or maybe the correct word for it is somehow I have a distinguished triangle. move the C over to this side. So I get to cone. Is it how it's written? Anyways, that's that. So you can think of it, I guess what to think of it is you have along that sequence of cohomology with C's and D's and the cones. Somehow the interesting part of the cone is that it combines the kernel of C and D and co-kernels of this map F into one cohomology. So that's the only way I think of it. And right, one more thing. We get to the exact sequence. But usually we use, let me write E for this for simplicity. It's called a fiber product. It's a fiber of this thing, which is a cone of F twisted by -1. So I shift it back again, so that this cone looks like the kernel of F. C goes to D, but it doesn't really matter. I mean, I don't know. It just somehow it's more conventional to define cone, but somehow fiber is, I guess, it's less written in the literature. Somehow, it's my understanding. Maybe it's wrong. So therefore, when you take cohomology, the common of E looks like the kernel of the map from the complex of C to complex of D, and then goes on to HI of E, HI of C, HI of D, and so. Okay, so somehow you can think of it as HI of E combine the co-kernel of the previous degree and the kernel of this HI. So it's combining it into one cohomology. Bless you. Oh, 这在美国养成的习惯就是有人打喷嚏，我们就要说 bless you， 改不了了。对，有人打喷嚏，你要说 bless you。对，对，不知道是为什么。Okay, okay, why do I care about this? Let me continue to review the cohomology part. Finish review the cohomology part. I'll come back to why I need to talk about this cone and fibers. I'll give an example. So 3. Given 2 complexes, C and D, and I can define fiber product. Excuse me, the tensor product. So I have, this is probably everybody knows this. Basically, when you have sort of 2 complexes, you can make it sort of 2-dimensional complex, and you direct sum all the things on the diagonal. So that's going to be make it 1-to-1 usual complex. It's the same thing as usual. But let me just sort of say a little bit about the sign. If you take D of X and tensor Y of something of pure degree, then that's the sign convention is that you D the first one, but then you this is you DC the first one. You D for the second one. You have to make a sign change by degree. So in particular, so given a morphism C dot tensor with D dot to E dot, we have natural cut product. From the ith cohomology and jth cohomology of D to I plus jth cohomology of E. Whew. Done with review for homological algebra of the things I need to use. So now, I'm gonna talk about the situation I want to consider. Okay, so if M is a finite length OE module with a continuous action by a profinite group. So I can define, let me write R gamma of gamma M. So somehow the point of working with complex is that we just work with complex. We don't take cohomology. We only take cohomology when we have to. So that's what I'm saying. So I want to write R gamma of gamma M to be just the complex of the things you're familiar with. Sort of the okay, because this is sort of C0, this is C1, so this is a continuous map from gamma to M. I'm taking a continuous cohomology in some sense. So this is in degree 0, and so on. This is a usual map D. This is how you define group cohomology. But I don't want to take cohomology. I just want to keep it as a complex for now. So this is a continuous chain for Galois cohomology, for group cohomology. And this will compute the group cohomology. And so HI of this R gamma of gamma M is just the usual group cohomology. Okay, I'll keep it as this. Now here's why I want to do this. So now I want to talk about the situation we discussed earlier. So let me write this. Again, now I want L to be greater than or equal to 3. Okay? Write this. So we talk about we can apply this situation to gamma equals the Galois group of F unreped away from S. But I want to take the, maybe I just write fiber now of R gamma of GFS. So I get the complex of continuous cochains for this M, but then I can always map it to by restriction. I have a continuous cochain and I can restrict the value to all the subgroups, all the direct sum of all the V over S of GFV. Somehow I'm taking you can think of it kind of a relative Galois cohomology of the global cohomology relative to the local one. Then in the same way, so sorry, here. I want to take V in, so SF, where SF is the places in S, but all the Archimedean ones I remove. Okay, because I take my L to be greater than or equal to 3, all the Archimedean cohomology, all take cohomology of the Archimedean place, all vanishes. Somehow I couldn't deal with those by the method I'm going to present. So I want to define, so HI, theta, to be just a cohomology of this guy. I want to say this is kind of a special case of so-called Selmer complex. A la Nicolar. Shoot. Forgot the accent. Never mind. I apologize to Yang. Forgot his accent. I should have known. Never mind. Okay, so we have this. So what does this mean? I mean, or like what does concretely mean in terms of cohomology? It means the following. So when I take cohomology, as I said, this fiber looks like the kernel of the map of the two complex. So this will go to H0 of the first cohomology, and then we'll go to H0 of the other one, which is direct sum of H0s. SF. But for our convenience, you see that if you want to write things that looks like the Prato-Tate exact sequence we have over there. So let's do this. I mean, so long as that sequence, I can break it anywhere I want. Right? H1 goes to, looks like H1. So if I take the cohomology, so that's precisely the thing that somehow takes the place of higher cohomology of the dual side in the long-term exact sequence. So we need to show basically H2 3 minus I of SF GFS M is isomorphic to HI of GFS. For Prato-Tate duality. Okay. So let me before doing much, let's sort of do some of the places. So first of all, I claim that the first thing I notice is H0 tilde SF. The reason I wrote it outside is because this is 0. This is because, what is it? It's a kernel of this map, right? And what is that map? That map is just taking GFS invariant of M, mapping to, I don't need direct sum, I just need one place. If I have just any one place, right? GFS is a much bigger group than the local Galois group. If I take the invariant of the much bigger group, it definitely sits inside the invariant of the smaller group. So this one already injects in one of the factors here. And of course, there is one factor, which is at least there's one over the place L. So this is injective. So therefore, this H2 to 0 is 0. So that's 0, really. And now the rest will take a bit of a time to deal with. Let's continue. So let me also say that, so the Euler characteristic formula namely, I want to compute chi of GFS M being the same as sum of all the. Because my L is greater than or equal to 3, I just have to do finite part of this. Right. Oh no. Sorry. I forgot. So hold on a sec. My bad. Yeah. So okay. Recall the Euler characteristic formula says this. The Euler characteristic of this one is the sum of the Euler characteristic of the local ones. And I can separate out the finite part and then sum over the Archimedean ones. Oh, sorry, the dimension of this. Oh, excuse me, I mean in the length, excuse me, of this thing. Okay? But now if you look at sort of the definition of the cell of this sort of, let me call it Selmer complex or whatever, Selmer cohomology. So this is you think it's a relatively global one with a local one. So therefore the Euler characteristic of the tilde one is precisely the difference of the two. So I need to show somehow the chi tilde GFSM is equal to length of M. So that's all I need to show for Euler characteristic. We give a final remark. When L equals 2, or proof somehow doesn't quite work, but we can still do things like this. So I can similarly define this as a false. So they, I guess there are people here who doesn't quite like me writing fiber. So let me go back to the more traditional or more commonly used notation, cone. I think it's good. We should go back to the sort of what everybody else uses. We're going to do sort of the same thing as what we had over there, but for Archimedean places. Of course, it only matters if the Archimedean place is the real place. Direct sum of that. So the local cohomology, instead of do that, I take sort of R gamma Tate of GFBM. By that, I mean sort of an infinite going both ways, long sequence. I guess, for example, this is degree 0, and this is sort of the complex conjugation minus 1, and this is complex conjugation plus 1, and then they alternate. So it's sort of extending both ways from positive infinity and negative infinity. And negative 1. So if you do this, then what we need to show is once again precisely that duality statement. S. Maybe I call it S. L. GFS. Maybe write this as I. The other one is 3 minus I. Doesn't really matter. Right. And you still have this. And but then maybe just a little bit. But you wanted to for all I less than equal to 3. In a sense, because see this cohomology will go both to positive infinity and negative infinity. So the term going to negative, so therefore this, I guess this Selmer cohomology will have negative terms. Those negative terms will really be dual to this cohomology, where of course this will become sort of positive terms. And this will be the same as the real cohomology will come somehow dual to the real cohomology coming out from here. But unfortunately, somehow I couldn't prove this for a technical reason. I'll try to explain later. But of course, if we admit the Plato-Tate exact sequence, this is true. But now we're trying to prove it. or rather somehow give maybe a slightly different proof of the original one. So let me think. So to prove, I guess the main goal is somehow to prove this, and that sort of will come later. So the first step is to construct a map, a natural homomorphism. Again, I'm going back to L greater than or equal to 3 from one to another. Or rather, equivalently, I want to get a pairing between the two. Or maybe, okay, I want to get a natural pairing, factorial pairing. So what I want to do is I want to consider the Galois cohomology pairing. So now let's do things more abstractly. So remember, the left-hand side is a cone of this. And now I want to pair it with this side. We know that all cut products come from sort of this kind of tensor product going to another complex. So let's just sort of do this on a completely sort of complex level. Now I can do a kind of a cut product. So this will go to cone of, so basically it will be this thing coupling with this inner thing and this thing together. So that's the benefit of working with relative setting is somehow automatically there's a map here, and if you take cohomology and then do the cut product, it's going to be a mess because you have to show that somehow the co-kernel and kernel of one thing and co-kernel of the other thing have to kind of connect to a nice module. But this is, if you do it completely on the compact level, there's no problem. You just simply do this because everything's factorial. Oh, I should have used parentheses, but anyways. Sometimes it's too much to write. So. Okay. Now I know that M tensor M dual 1 goes to E over O 1, right? So this is just, let's write this. Fine. I'm going to change this in a bit. If you're copying, so just stop a little bit because I want to save some space. Okay? And we know what E1 is, so I'm going to rewrite this as mu L infinity. This is mu L infinity. And then outside I tensor with O. Okay. Just save some space. I mean, at the end of the day, I wanted to cup at very end. I want to cup it to O over E over O. That's the end goal of this long calculation or long defining cut product, or not, or maybe I want to get to something whose H3 is going to be, so H3 of that is going to E over Q, and then I will have to Hi of this one copying with H3 minus I of that one going to H3 of the end thing, which is that. So that one. Okay, you have the mu infinity, mu infinity. Now, there's a natural embedding of, we know that the mu infinity, well, definitely, for the global one, I can definitely embed into the global units. And for the local one, it will embed to the local units. Not units, but local elements. So this map corresponds to global cohomology. We embed the L power torsion into this thingy, and this embed local one into here. Once again, this is an indication of why I wanna work with relative cohomology, which is somehow. I mean, otherwise, if you take cohomology, this column maps to here, and this column maps to here. But why does sort of combined cohomology of this map to the combined cohomology over here? So save the trouble of discussing the extension classes and stuff. So now when you have these two, you can now start to kind of combine them. Because we'll have you can just sort of quotient this into here. Let's see. So this will just basically go to maybe S. We have an exact sequence S. This is just quotient. I don't know how to write it. So this is actually isomorphic too. Oh, actually, this one. This is good. Then I have to be a little bit careful here. Twist by. I'm taking the cone of this. I always got confused. Cone is like the co-kernel, so this is it. So it's like taking the co-kernel of this one. So I'm just basically taking the co-kernel of this one. Okay. But we know that H2 of this thingy is equal to I believe H3 of, I'm sorry, I want to say H3 of this thingy is equal to, because of the twist, it's really H2 of GF of OFS 1 over S cross of. And this is what we talked about earlier. Maybe let's just sort of take ZL. This is just QL mod ZL. Or maybe if I want a tensor with O, that's going to be E over OE. E over O. So recall that this was a class field theory I introduced. This is a class field theory input I discussed at the beginning of this lecture. Yeah, Archimedean part, that's why I need L greater than equal to 3. Archimedean part only contribute two torsions. Because R cross is all divisible. Because R cross this is all divisible. The only thing that's not divisible is the 2 part. I forgot to say that. Sorry. Thanks for the question. Yes. Maybe I should have used F here. Somehow. I mean, I guess both sides, there's a 2 part missing. The Archimedean part missing. But that only will create a 2 torsion. But my coefficient is greater than equal to 3, so there's no problem. Other questions? Okay. Good. So we have this thing. So if H3 of this one is equal to the dualizing sort of object, then I get perfect pairing. No, excuse me. Get a pairing, not a perfect pairing yet. H choose I as F. I mean, of course, sorry, there's no dual here. Of course, then you have mapped this one to the dual. When L equals 2, you can make a similar argument where somehow the Archimedean place can be fixed. I mean, namely here, you put in some sort of Tate things here. I think I calculated myself, and then this can be fixed. You do get a pairing. It's the next step, showing it's an isomorphism, what gets in trouble. Okay. So step 2. I want to show that I don't want to write it again. Sorry. This natural map is an isomorphism. Okay, it's the same thing. I don't want to copy it again. For this, I want to employ exactly the same argument as in the local case. Case. So basically, I reduce this to, I mean, by the cohomological argument I used. So just need to show when somehow F contains F mu L, and also my M is the trivial representation, or the same thing as mu L. It's enough to consider this case. Because once we've done this case, we have this sort of cohomological argument I'm going both ways. And let me mention that when L equals 2, this calculation I'm going to do now, so this special case, this argument works. But it's the cohomological argument in the local duality case doesn't quite work. Because in that case, in the local duality argument, I really need my sort of the two things here and here. They're sort of both bounded, or at least one of them is bounded. But somehow when L equals 2, neither of these is bounded. Somehow I only get to show the injectivity, but I couldn't prove the. I can prove the surjectivity, but not the injectivity. Somehow. So I couldn't get that part to work. I did spend a lot of time on that, but somehow. So let's do this part of the calculation. So in this case, I want to compute, basically I want to compute both sides. Guess there's no escape here. But I mean, but of course we know that computing retrieval coefficient is a lot easier task than other things. So this is the, I choose on the tutor side, I choose to use mu L. I guess maybe, anyway, let's compute this part. This is the cone of R gamma going to right? So by Kummer, I mean, I should have write another com inside, but let me just sort of write a complex here. Because this mu L is precisely the kernel of this thing. So in the derived category sense, I can basically replace it by this complex, and then take the corresponding continuous code chain with values on that complex, and making that into one complex, and then take cohomology. That's the original one. Okay. So this is the flexibility when you work with completely compact without taking cohomology. You just formulate that. That's because, and also as I said, I really need to use an integral version of the multiplicative group. Otherwise, this will not be surjective. And locally, I do FV bar. Now I combine the two together as before over there. It's a product of I mean, maybe just L. I don't know what. It is raising to L's power. Hold on a second. So this is a cohomology. Oh, there's no cone anymore. My bad. There's no cone anymore. Just that. Inside the registry. So this is a bigger one. Hold on a second. If I take cone, I still have the -1 here. Okay. So I basically combine the two together. So so it's like when you have sort of A goes to B complex, go to A prime, go to B prime, right? You can think of as the cohomology of this one going to cohomology of this one, or you can take the cohomology of this one going to cohomology of this one. So this is like this going to this one. You could do it vertically. So this first go to here, and this first go to here, and then go horizontally. Okay. You can play the. Okay. I still feel bad not telling you this, but let me point out here. Maybe I'm not sure if this is one of the confusing points here. So the reason I wrote this but not that is because I have a base f. Up here I have a fs, right? I have a v here. In general, I should have infinite many places up here. And whereas over here I only take one of them. So here's a Shapiro-Lemma thing going on here, in the sense that, so over here, so I'm really taking the product of all those things above here. But my group cohomology is with respect to the big group, G. By Shapiro-Lemma, it's like so here I'm using the following thing. Hi of GFS of product of all the places above that of FSW. That's the same as HI. Is that clear? You can see this, right? Of GLV of cross of FB cross. I'm using this Shapiro-Lemma here. So therefore, I can replace a local Galois cohomology with a global one at the expense of sort of doing kind of an induction. So they're subtle here. And also earlier, I kind of hide it in this step over here. Earlier, I hid it in the step over there. I know that somehow. I was trying to not to talk about it, confuse you further. But anyhow, hope this doesn't confuse it as much. It's a choice of telling you the truth or making things a little nicer to you. But let's recall that HI of GFS, of this cohomology, we already computed it. So this is tensor ZL. Oh, right. I mean, I'm taking L torsion anyway, so that's okay. So that's two things. One is this global thingy. And QL mod ZL if I equals 2 and 0 otherwise. So I can compute that I can compute this term because I know the coefficient of this one. This is just a multiplication by L. So I get so let's use long exact sequence computing this. So I have H1 to the SF. It's this cohomology over here. This will go to because of the shift here, because of this -1 shift here. It turns out this will go to H0 of G mod F of that thingy. Oh, I remember I denoted by ZFS, right? I think I denoted by ZFS. Anyhow. But let me use the explicit version of this. What was the second? Over, no, not that one. What am I right? Oh, yeah, it was V not in S, O, F, V cross. Okay, so it goes to that. And this multiplication by L, same thing. Right? Now H1 is 0, so good. That was easy. H2. H2 is H2. This is QL. Oh, excuse me. Did I tensor? Well, no, sorry. I don't need the O. Never mind. And everything else is just 0. Because, I mean, this multiplication by L is surjective here. So whatever that is, and it's all 0 down here, so everything is 0 down. Okay? So we've got this. That's the tutor part. So let's see, what do I want? Oh, excuse me, this is 2. Okay. So, I'm bad. This is 2. This was 2, and this was 3. Degree is shifted by 1. It's confusing. So what do I get? Let me pick out the information that's useful to me. Somehow the first one is a little bit difficult to compute. I guess I could compute it, but somehow. Let's don't compute H1 to it yet. Let's do 2 and 3. What is that? This is the co-kernel of this thing. Let's do 3. 3 is easy. Let's do 3. H3 I know. It's the kernel of this multiplication by L. It's just FL. Okay? And that's precisely, not precisely, I think there's only one way to kind of make the dual. Because I wanted to show that this third column is isomorphic to the zeroth column already. And zeroth column is just basically constants. And you can show that this is not only this corresponding map, it's just, you have not only these two are sort of the same, this is FL, of course, same thing. And some other cut products is essentially given by somehow on this side, basically copying with H0 here, and the H3 is the same calculation. So this is an isomorphism for the H3 here and H0 here. Right. And let's do the H2. Because I'm in a weird situation, I don't know how to do. H1 is a little bit difficult to control. So that's okay. So maybe let's see on the other side, because I want to show this H2 tilde is dual to the other H1. So what is H1? This has trivial action on FL. So that's just a hop. Dual. I don't even know how to write this. This is just, if you harm this, it definitely factors the abelian quotient. And then quotient by L, because the target is FL. And now this looks like just a dual to itself in some sense. So it's just nothing but G abelian FS just itself, because I have another contracting dual here. So just that. Now by global classical theory, what is the sky? This is just sort of F bar. So by global classical theory, without the unrefined at S, this is just sort of this quotient on the left. Global, sort of a del mod F cross, and then the sort of real part, kinetic part of the real part. And because you want it to be unrefined outside of S, so you have to kill all the inertial groups away from S. And that's pretty much what we had over here, in the sense that this is the co-kernel of this map. This thing, also mod L, so this thing mod L. If you look at this and what we have over there, they're precisely the same. And of course, I'm using L greater than or equal to 3 here. And Archimedean place, and just I'm very sloppy about Archimedean places, but it's not, I'm talking about L torsion. So that's my shoot. So that's an isomorphism. So somehow I proved this, but somehow the H1 is a little bit difficult to. This one I can compute, I guess. But then this H2 is a little difficult to compute. So I guess the only way I can think of it is I want to return to prototype. So what I'm doing is that, let's write down the prototype, unfortunately. But so I, that's right. Take a bit of time. let's see. I mean, what are these computation? What does this computation give me? Well, give me this bit here. Remember that you always have these maps. And I guess this isomorphism, so this H1 star, so this is this thing, it's going to be, what we showed is the same thing, H2 tilde SF, and blah, 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 right? So at least we see that from this term onwards, the partial exact sequence is done, is proved. Except this term is a little different. I mean, in general, for group Coleman, it's a little difficult to control what H2 does. So at this moment, I proved sort of the last part of the partial. But remember, when we introduced partial exact sequence, I said one thing, that this partial exact sequence is self-dual, in the sense that if you dualize each of the modules and then dual the exact complex, it will become sort of itself. And also, and so therefore, if you know the last part being an exact, you can dualize it. Actually, I think you get to here. If you know the last part being exact, then you dualize it. You show the previous part being exact. With the catch that, under my assumption that F contains F mu L, the FL is isomorphic to mu L. So whenever you prove something about mu L, you get it for the FL version for free. So therefore, if you dualize the entire exact sequence, and then somehow you get the previous part being exact, and that will tell you this star is isomorphic to whatever the Selmer cohomology you wanted to show. So that's it. Use the natural kind of a self-duality of partial. Okay. Good. Let me just sort of comment one thing, that because I'm teaching a course, and I feel like most of you, this is the first time for you to see partial long exact sequence and local Tate duality. I think it's important that you at least see, I guess, one version of the proof, even if it's not very complete. But of course, in reality, is that in practice, you're not going to go into the proof again. You just use whatever is given you. You just need to apply it, learn how to apply it. So I understand maybe this could be quite, it seems very difficult to you, but somehow when we get to applications, it won't be like that. It will be easier, I think. Okay, I have about 10 minutes. There's no way to do it. Oh, the characteristic, but let's try. Let's try Euler characteristic. Again, by exactly same reduction. We'll consider the following situation. We just have to consider the following. So L over K. So remember that my F is down here. So this is my G. I use Artin's theorem, or I don't know what's for L, Artin's theorem, to reduce the case where H is cyclic of order prime to P. To L. And also I can always assume that L contains L roots of unity. And my module M is induced from H to G of a sort of H module lives over here. And I want to compute chi of the tutored version. And basically this will be the same as computing it on K. Or rather maybe on L. So let me just write down what. So computing this will be same as computing on H, and because this index of H is the coordinate of H is order prime to L, so I can maybe let me just write it one more step to S K F G K S K of N. And what that is also the same thing as sum over I from 0 to 2 of minus 1I of dimension over FL of, and also I want to say N is over FL, vector space. Right, forgot that. And this is H2 to I SL F of GL SL mu L. Tensor with N twist by 1 and H. So basically, I want to compute this thing here. It's like a local case, except that now I'm in a global situation. Right. So now, let's see, what do I want? Already computed, shoot. Shoot, I already computed this somehow earlier. So I already erased it somehow. Gee, my bad. This is very bad. So I already computed somehow H2 to SF of GFS mu L. Or like in, okay, let me use this SL F GL SL mu L. This is equal to, for I equals 3, I have an FL here. Okay? And for, oh my bad, so sorry. So this is, so this should be x from 0 to 3, because h0 is 0. Because I shifted by 1. So I do h0 and 3 here. And basically other things, so h1 and 2 are, so basically kernel of this F cross, L cross now, AL cross of product of B naught in SL, OLE cross, going to multiplication by L to the same thing. This is when I equals to 1. When I equals 2 is the co-kernel of this thing. I just somehow, remember that I had on this board, I have the exact sequence where this thing goes to this. Anyway. Right, so let me give it a name. So let me call it ZL SL, okay? So H2 to 1, omit all the coefficients. So this is the kernel of multiplication by L of the ZL SL goes to ZL SL. And H2 to 2 is a co-kernel of this guy. So whenever you see a kernel and co-kernel, you know that somehow they comodular, they kind of cancel each other. H2 to 3 is FL. So I just have to understand what this thing is. So here's what it is. Let's analyze this thing. So this AL. If I put in product of all the V in S, L, F, O, L, V cross. Okay, let's do the Archimedean as well. I don't have to do the Archimedean somehow. So this one, if you map that into here, I will get an ideal class group of OL. So this will, so this Archimedean place will kill the Archimedean place in the Adels. And these finite places will become, now this will be quotient all the integral parts of the finite places. Now this quotient is typically known as the ideal class group. Whereas the kernel of this one is clearly the group of units. Okay? And I want to point out this is finite. And so therefore, when you do this multiplication by L, one of them takes kernel, the other one takes co-kernel. The contribution of this one, this has no contribution. Right, because one of them goes to H1, the other one goes to H2. And one is kernel, the other one is co-kernel. And so regarding these, so let me write what I have. So chi SF, you have several parts, which is that somehow the Archimedean component. Once again, this has no contribution either, because my L is greater than or equal to 3. Archimedean component has no contribution whatsoever. So that has no contribution. Basically, all the contribution come from this and this. If I got it correctly, so let me say, let me write this. So it's going to be the product of V in SLF of OL V cross. So because this cohomology will give me this bit here. Now I have to, so basically I want to, let me write the first term out, and then, so this is going to be the dimension of the product of OL V. Let me use this term here. So this is OL cross tensor with n minus 1 H. I should be, my bad, I'm sorry, I'm very sorry. This is going to be the dimension of kernel of OL cross times L, OL cross tensor with n minus 1. The contribution of this one minus the dimension of co-kernel of this thing, OL cross times L. This writing is annoying, right? If you think about what this thing, or this term, contribute to this, or the characteristic, it's just really this thing. Okay, it's just so long to write. So let me summarize what that is. It's by writing as chi H. No, I want to finish this. Okay, I'll finish next time.